Okay, so let's get started. The first question is shown here. It's about a flute. So we're told to consider a 65 centimeter long Western concert flute. We're given a speed of sound. And we're told that the lowest note that this flute can play is C4, and we're given an actual frequency for that, which is good because frequency is what determines the sound that we hear. And we're simply asked, the entirety of the problem is just determine whether we should consider this flute as an open pipe or a closed pipe instrument. So what we're getting at, do we want to consider this as a we have kind of two different sets of equations in physics for standing waves, and standing waves are kind of what occur in instruments and produce sound. So we have the first kind of, the physics is the same if you have an open or closed end condition. What that might look like is, in the first case, you might have a standing wave that looks like this, if this is the length of your instrument. In the closed case, it's just kind of the same thing, just shifted by a quarter wavelength, something like that. So hopefully that's really, and as you guys remember, the kind of the math and the physics behind all of this is the exact same. So you find things like lambda is equal to 2L, L, L over 2, stuff like that. Sorry. Yeah, let's just stick with lambda is equal to 2L in the fun mode, because that's what we're concerned with for musical instruments. The completely different setup is when we have an open-closed situation. So the fundamental mode will look something like this if we have an instrument of length L. And in this case, lambda is equal to 4L. So you can picture that this kind of bit here is a quarter wavelength. So we'll kind of go all the way down and then repeat here, and that's where the wavelength would fully repeat. So basically what this is getting at is asking, should we, if we have an open pipe or a closed, what this is really asking is it this case or this case, is what I'm not very musically inclined, so I've never played one, but you have a hole up and the person that's playing the instrument puts their lips here and they excite a vibration, and the vibration goes in the tube and you get some sort of standing wave. So it's kind of open at, what do we have here? Do we have open or open closed? Kind of, do we want the case on the left or do we want the case on the right? And to figure this out, what we're told is to consider this note C4. So this is a fundamental mode. And all the kind of notes that we consider for musical instruments are the fundamental mode. That means M is equal to 0 or 1, depending on your counting system, how you like to count those. If you start at 0 or 1, I guess 1 is probably added, is probably more clear to you guys. Yeah, so John posted in the chat about having trouble hearing, so that's super important. So if you guys are having trouble hearing, please let me know. I can try and fix that on my end. Hopefully Calvin speaks for everybody. Okay, we've got a few people that are confirming. So yeah, sometimes just kind of closing down the collaborate session and jumping back in resolves a lot of stuff. Okay, so fundamental mode, we've got a frequency of 261.63, and that's in hertz. So basically all we need to do is we'll try and solve, we kind of have everything. We have a wavelength, we have a speed of sound, this is 353, and we have a frequency. So kind of the equation we like to use with waves, speed is equal to the wavelength times the frequency. We have all the components, so we'll just choose two of them and calculate the third and double check with what we're given in the problem. So what I'm going to do is I'm going to calculate the frequency. There's no real reason to do it that way. It's not easier or harder. It's just seems nice to me. So we want to calculate the frequency. That's equal to the speed of sound divided by the wavelength. Let's do case 1, where this is equal to 2L. So what we end up with is that the frequency is equal to the speed of sound divided by twice the length of the flute. And at this point, we can just fill in the numbers. And unlike last week where I got lazy and didn't do any calculator work, I'll include the answers here because it kind of makes a difference how we interpret the question and the answer. We actually need to know the numbers. So I'm going to convert the centimeters, which are the length of the flute, into meters just for convenience. And what we'll get is approximately 269 hertz. And case 2, which is where we had the open-closed condition, 4L was our wavelength. The frequency is then velocity divided by, or speed divided by wavelength. Wavelength is 4L, as I just said. And we just plug our numbers in again. And the only real difference is this number right here, the 4. The length of the flute is still the same. Speed of sound is still the same. So basically we get half the answer we got over here. 134 and a half, I think is what that is. And we compare these to the note that we're kind of working with, 261.63. And this is clearly the closest to that. And we only need to find closest because some of this stuff in real life is imperfect. If this is exactly what C4 is, we might be a little bit off. We might not be counting if this is the whole length of the flute, but maybe the end is here. We've got a little bit too much length or not enough length, that kind of thing. So it's imperfect, but the idea is that this is the one that matches. Okay, so this is a really neat problem. It's pretty similar to a lab you guys would do if you were doing labs in person. I don't really know what Professor DeVette has in store for you guys if you're doing this from home or virtually or whatever. Not too sure, but it's kind of similar. A shame you don't get to do it in person. So we've got an attached diagram for a Cuenca tube. So that's shown here. The description here says we've got a source of sound. That's a tuning fork in this case. And that just vibrates. And as the fork vibrates, it vibrates the air. Vibrations in the air, if they're in the right frequency, we can perceive them as sound. So it's at one end here. There's kind of this inlet to the pipe system. At the other end, we've got kind of an outlet, and there's a detector, we're told. And there's two paths. So the sound can come in, and it can either go in the right path or the left path. And the cool thing is that the right path actually is just composed of two parts, and this can extend and move to the right or to the left if it's in an extended state. So what happens is basically we have some of the sound going through path 1, and it just has, I'll call this distance 1. Because the left side can't change, distance 1 is kind of, it's fixed, it's constant. And then the other, kind of the, however much goes through the left, some amount also goes through the right, or an equal amount goes to the right. But it has a different path, D2. And these recombine. And if there's any kind of path difference, so right now we'll already call this, sometimes it's delta D, delta X, delta Y. It might get a different variable, but as long as you understand what it means, you guys should be able to handle it. I'll call it in this case delta D. So there's a path difference. There can be either constructive or destructive interference if that path difference is equal to a multiple of the wavelength or a half multiple of a half wavelength, respectively. So with that in mind, I think it goes through this. It says extending the tube, the detector measures both maxima and minima in the output. So what that really means is imagine that the tube, as you move it, if you make the path difference equal to m being some integer times lambda, then you'll get constructive interference. We'll just put C there. And if you keep moving the tube further, and you have the path difference between the left and the right side be equal to a half integer, multiple, you get destructive interference. It's C, not an E, in case that wasn't clear. So what happens is as you move this to the right, you keep moving and maybe you get constructive. You move to the right more, you get destructive. You move to the right again, you get constructive, and so on. And you could imagine that this is m equals 1, um, m equals 1.5, m equals 2. You get destructive at 2.5 and so on and so forth. So this is just a kind of a, you use sound as your wave, and this is just a method of splitting the sound up into two paths, and you can make one path longer, and you can get constructive and destructive interference as you make the path difference perfect. And kind of in between these states, when you have neither constructive or destructive, you're just somewhere in the middle, and it's not so well defined. Okay, so I think we're ready to look. We kind of, hopefully that's a good explanation for how this works. Maybe a little bit more easy to digest than this first bit, but I think we're ready to look at what question A is actually asking from us. Yeah, so we're extending the tube, and we, like I said, we get maxima, we get minima, that kind of thing. And suppose you're actually doing this experiment and you record the data that you measured, and what you would do is you would record the interference order, so that's this M that we kind of indicated here. That's our independent variable, and the dependent variable would be how much we had to extend the tube to find that X. So just imagine you have a table of values, you're doing this experiment in the lab, you're looking for the first constructive interference, and you have to extend the tube, and you end up measuring X. Maybe you measure X with a ruler, that kind of thing. So you would find X1, X2, that kind of stuff, and then you would make a graph. And you would have a data point here, and here, and here, and here, and here. It will look something like this. And with these points, you could figure out what this slope is. And what we're told in the problem is if you did all of this and you constructed the experiment, suppose that the slope is equal to 2.157. The first part says find an expression that's equal to this slope in some kind of variables that might relate to interference. And we're asked to determine what the units of this slope should be. So I'll work with, because this says constructive interference order, let's use our equation for constructive interference. So the path length difference between the left side and the right side, we'll call that delta D. That's got to be equal to some multiple of the wavelength for constructive interference to occur. Now, what exactly is delta D? And how much is it changing? Well, let's assume that this is the left side and the right side are equal when the left side is fully kind of shut and moved into the right before it's extended. So as you move some amount X here that's already labeled, it gets X bigger along the bottom. It also gets X bigger along the top. So if you change the path difference by moving the tube some amount X, you've actually made the path longer by 2X. So that is 2X times lambda, or sorry, 2X equal to n lambda. And now we need to ask ourselves kind of, can we sub in something for the wavelength? And do we want to do wavelength? Yeah, I think, yeah, so what I'm going to do, this question is perhaps a little poorly written. If you notice here, there's some more information that we're going to use later on. We've got notes in frequency, and we've got a velocity that we're going to use, and we're going to be dealing with frequencies and velocities. So what I was kind of going over is, do I want to change right now? So what I'm going to do is I'll change from wavelength into velocity and frequency, right? We know that wavelength is equal to velocity divided by frequency. So I'm going to make that substitution. I think it's useful to do now because we can use that a little bit later. Okay, so now I think we have all the variables that are going to be useful to us. The last thing we need to do is we want to figure this out in kind of this is a line, we have a slope, we want to get it in the form that looks kind of like y equals mx plus b, where x and y are very generic, but this is our independent variable, and this is our dependent variable. So we're told here that m is independent and x is dependent. So we just need to manipulate this equation here a tiny bit so that we have x looking like our y. Sorry, m looking like our y. So this will be equal to m equals 2f divided by v is equal to x, or sorry, times x. So this is kind of like our y, this is our x, thankfully x is the same, and this term in here is our slope. I'm just going to make a bit of space. So our slope, the thing we're trying to find the expression for, we already know it's 2.157 is equal to 2f over v, and it's perfectly okay to write the word slope. We don't need a fancy variable for it. Traditionally, m is used like I have here, but we already have an m doing something else, and if we use m, it'll just be very hard to keep track. So we have our slope, we found our expression, that's the first part of the question. We want to figure out what the units should be. So 2, we can just look at the quantities that make up this. 2 has no units, it's just a number. We have hertz divided by meters per second. We can simplify that a bit because hertz is actually the same as writing one, it's a reciprocal second or 1 per second. So here's per second, replace hertz, so these go away, and it's 1 over meters. So our units are just reciprocal meters or 1 over meters. Okay, so we're told to assume that the tube is perfectly built when the right side has 0 extension. We find constructive interference. We can also assume that the left side and the right side are perfectly the same length, but that's not exactly necessary. So how far must the tube extend to find the third minimum is what we're asked. And this is a really tricky question because it says minimum. So what we've been doing with A is we've been considering when the maximums are happening. We originally used D is equal to m lambda. We can't use that this time. We want delta D is equal to m plus, because we want things like lambda over 2, 3 lambda over 2. We want these type of path differences. When that happens, in case you guys are having a hard time visualizing it, when our path differences are half wavelength apart, hopefully that's a decent drawing, we get waves like this that add up into nothing. Notice the crests, troughs, all line, and sum to 0. So that's kind of what we're looking for. And from this point to this point here, it's a half wavelength difference in terms of what the shift is in x. So just in case this is hard for you guys to visualize or you're forgetting where this came from and you want to know why I'm focused on having half integral multiples of the wavelength. So let's kind of do what we did before, but we'll proceed with this equation this time. So delta D, remember that any amount that we move the tube, delta D, if we move it x, we pick up a path length difference of 2x. We can do what we did before, replace the wavelength with the speed divided by frequency. And what we're trying to solve for is how far must the tube be extended? We extend the tube in amount x, so let's solve for x. So this is looking pretty similar to what we had right here. It's a little bit inverted. but this quantity that we call the slope 2f over v is actually on the right-hand side here. So what we can actually do is simplify this and say m plus 1/2 divided by the slope. So this is an equation that gives us the location, how far we have to move the tube to find the minima. It's a minima because we started with the equation for destructive interference. We're looking for locations of destructive interference. And one thing I struggle with, and I think a lot of students struggle with, is keeping track. Does m start at 0? Does m start at 1? I usually just like counting it out. So the smallest x that we can get is, you could start counting, because we've used plus, you can imagine the smallest number that goes in here is 0 for m plus 1/2. That will be 1/2, 1 plus 1/2 is equal to 3/2, and so on and so forth. So you see how the next one will be 5/2, etc. You could write this differently, and I don't know what Professor DeVette gave to make sure you know what he expects, but you could also get the same thing if you have m minus 1/2. And instead of starting at 0, you could do 1 minus 1/2. That gives you 3/2. Or sorry, 1/2. 2 minus 1/2, do 3/2, etc. So if you want counting at 0, you can use a minus. If you want to start counting, or at 1, you use a minus. If you want to start counting at 0, you use a plus. I think you guys should be able to get that. Not too hard to understand, but make sure, go back and see what Professor DeVette gave you guys in your lecture notes so that you guys know what he wants. It's just in case anyone's sitting and watching this saying, where does this plus come from? It could easily be a minus, and I'm just not sure what Professor DeVette gave you guys. Okay, cool. I'm glad I got it right, or consistent with Professor DeVette. Neither one is right nor wrong. Okay, so we have this equation here, x, interference order, and we divide it by the slope. So like I said, our first 3 terms here are going to be 1/2, 3/2, 5/2. So just really to beat this to death, this is going to be the destructive interference that we measure. This is going to be the second order, the second one, and this is the third. This question is asking for the third. So we want m plus 1/2 to end up being 5/2. That's what I'm going to put in right here. So we can even call this x3 because it's the third destructive interference. We'll have 5/2 divided by this slope that we were given in the original problem. Plug all that. We get 1.159, I believe, meters. So what this really means, remember, x is just the amount the tube moves, so we have to move this 1.15 meters to the right, and actually the path length of the tube will get larger by 2.3 meters or so. The path length is double what the extension is. Okay, so that was a little bit drawn out, but I think hopefully it's clear for you guys. We're given a table of music notes and their frequencies we're told, and we're asked, given that, so that's this table right here, the text is a little bit small, but we're given A through G, kind of a mismatched part of the scale, but we have all the notes kind of from A3 up to G sharp 4. We need to kind of figure out what the frequency is based on the slope and the speed of sound, and actually pick what note was assigned to this tuning fork. So we can, which one do I want to reuse? I guess we have V and we have F. Do we have F? I'm going to solve for F. I'm just trying to look at which one of these equations we want to use. drawing a bit of a blank here. I'm wondering if when we put this question together, we did not give enough information. So bear with me and give me a second so I can perhaps figure out exactly what I have written here in my notes. Okay, so we have the slope. Oh, okay, I think I know where we're. Yeah, okay, we're good. Yeah, so the slope is equal to twice the frequency divided by the velocity. These are the quantities that we were given. This is why I switched from wavelength to frequency over velocity. So I did something clever earlier and forgot all about it. So what we want to solve for is the frequency. The frequency is equal to this slope that we were just given in numerical form times the velocity, the speed of sound, divided by 2. So it's 2.157 was just the given in the problem. The speed of sound we're told to use is 343, which is the standard value. And the 2 is just kind of what came out of problem A. So we plug this into a calculator and we get 369.9 hertz. And all we have to do is we take this value now and we look up along here and we find this is F sharp. So that's the tuning fork. Yeah. Okay, so I think this is actually, did I only give you guys 3 problems? Yeah, we only gave you guys 3 problems this week because like I said, I think we did a decent amount of music stuff last time. It was maybe a little bit ahead of the homework in the lecture, just a tiny bit. So we just have a 3rd problem for this one. So this will be the last one. So if there's any lingering questions from the previous problems, don't forget to put them in the chat. So this is a problem focusing on ripple tank, or kind of the context is ripple tanks. We have 2 beaters. They're 18.1 centimeters apart, and they create waves with periods of about 1/3 of a second. So we're asked, what is the phase speed of the water waves in this tank if the 2nd order constructive interference fringes have an angle of 25.3? So I hope that there was I don't know, a demo or a video of a demo or something like that. But usually ripple tank problems, we draw them from overhead. There's 2 beaters or bobs. They're usually spherical and they go kind of up and down. So in this view, since we're looking top down, up and down is out of the page or in and out of the page. And they create circular waves. So what I'm drawing now, I'll even switch colors for the other one to make it kind of clear. So this is spatial. So this drawing, it's in kind of, you can imagine it's in space. So these differences here are equivalent to a wavelength. And the same thing happens with the same frequency and no phase difference at the other one. So you can see that there's places, maybe I'll switch to black again, where these 2 waves overlap, and there's going to be some sort of interference there. Here, and so on. So we usually assign the distance between the 2 sources to be d. We've been given a few other parameters. We have the period, 0.34 seconds. The actual value of d is 18 centimeters. Quickly convert that to meters. And the angle of the interference fringes is 25.3 degrees. So what this means is basically if I drew this nice and accurately, you have interference fringes that kind of, you have points where the constructive and the destructive interference, this is a bit spread out, my drawing's bad, and you have some sort of angle theta that these go at, and you have the m equals 1, 2, 3, and further out, you get larger interference order. So what we're told is that we have the second order fringe at 25.3 degrees. So kind of the master equation for these type of interference problems is d sine theta. That's your path difference. And if we're looking for constructive interference, we know that that path difference has to be equal to m lambda. If, we can even make note of that, this is for constructive interference. If we were asking about destructive interference, the idea of the path length coming from d sine theta, which is from trigonometry that hopefully Professor Devet has done on the lecture. It would take too long to kind of show you guys here, prove here. But this is a path length difference on the left side. If you were looking for destructive interference, you just change the correct path length on the right side relative to like how many lambda 2, lambda 3 lambda, or half a lambda, 1.5 lambda, that kind of thing, the wavelength. This is for destructive interference. But we're not going to use this one here because we're looking for constructive interference fringes, as mentioned in the problem. Okay, so we don't have the wavelength, but what we do have is a period. And of course, if we don't have a quantity like the wavelength or the frequency or whatever, we can mess around with V is equal to lambda F to hopefully find some quantities that we do have. So the wavelength is equal to the speed of sound divided by the frequency. We don't actually have the frequency, but we do have the period. And the period is related to the frequency as they are reciprocal quantities. So F is equal to 1 over T. So we have MV capital T for period, not tension. There's no tension in this problem. So at this point, we want to start working towards what we're actually the quantity we're interested in, which is the speed of the water waves in this tank. So we start to move everything to the other side. And at this point, we're basically done. We just need to put all those in, put them into a calculator. So this is D is the distance between the beaters. You will get different geometries as you guys move forward. If it's two sources of water waves like this, or if it's a double slit experiment with light going through it, if it's a refract or diffraction gradient kind of thing, if words are sounding a bit funny, it's just stuff that's coming in new lectures. The point is at least be aware of what D is in each of the different geometries and what it physically represents. So 25.3 is our angle. We have the second order fringes, and the period was 0.34 seconds. And already, I think I haven't mentioned it much this time, but I mentioned it a lot last week. Notice we have meters, something that's unitless, something that's unitless, and seconds. So we're going to end up with units of meters per second. We're looking for a speed, so everything makes sense. If we gotten something different, if it was like seconds per meter, we would have made a mistake somewhere. So always good to do these checks. And I think if I've done the calculator work right, we end up with a little bit over 1/10 of a meter per second. So relatively slow. I think I misspoke here. I said speed of sound. This is the speed of water waves. It's not the speed of sound. It's just the speed of, you can imagine when you go to the beach, right, and you watch waves of water come in, there's a certain speed at which they travel. This is that kind of speed. So 10 centimeters a second, 11 centimeters a second, that's pretty practical for something like that. If you were indeed looking for the speed of sound, usually they're in hundreds of meters per second. Okay, so I think that's all I have for you guys. I'm happy to take any questions, but if not, I think we all get to kind of sign off early. So I'll hang around for a little bit, let me know. But if no questions, then I'll see you guys next week. Oh, nice, a question. So Justin had a question, maximum particle speed practice midterm. I'm not familiar with that, but if you want to give a go of describing the question in the chat here, I can give you my opinion, but I haven't really taken a peek at them. Will we be discussing midterm questions later in class? I'm not sure what Professor DeVette has in store. I imagine the midterm questions will be available, like the solutions will be available at some time, so you can figure out what's wrong. I don't know if he has plans for me to go over them. I haven't heard of them if he does. Um, but there will be an announcement and stuff like that. I think it takes a little while for the questions to get marked, so I wouldn't expect to learn, like the solutions won't be available until the tests are handed back. I wouldn't think. But yeah, sorry for not having any more detail. You can always email Professor DeVed or to check if it's something that's really pressing.